Let's now move on to sample problem number 7. So we have a simply supported beam which has a span of 6 meter and carries a uniform dead load of 12 kN per meter and a concentrated live load of 40 kN at midspan. Design the beam for flexure alone using NSCP 2010 or 2015. So gagamitin nating provision is 2010 or 2015. And with that, i-design natin yung beam for flexure lang. So hindi natin i-design yung beam natin considering yung shear at saka yung deflection. So flexure lang tayo magpo-focus. So with this one, meron tayong mga given na mga service loads or yung mga unfactored loads natin. So meron tayong unfactored load na live load na 40 kN, uniformly distributed na dead load which is equal to 12 kN per meter. And ngayon, gagawin natin sa pag-design sa beam natin, we will make the service loads factored loads. So for this one, mag-a-apply tayo ng mga load combination para makuha natin yung mga factored loads natin. So let us now calculate for the value of your factored loads. By NSCP 2010 or NSCP 2015, yung load combination natin, that will become yung ultimate, that is equal to 1.2 dead load plus 1.6 live load. So with this one, kung kukunin natin yung WDL natin, so that will be WU. Kasi nga naka-ultimate tayo. Kapag meron kang subscript na U, meaning to say, kailangan mong i-factor yung load natin or naka-factor na yung load natin. So we have 1.2 multiplied yung dead load natin na 12. So you will have a value of 14.4 kN per meter. So meaning to say, since naka-factor na yung loads natin, ito yung gagamitin natin sa pag-design. Okay? Next, yung PU naman natin. Since yung PU natin, that is live load, so yung multiply natin dyan is 1.6 dun sa service load natin na 40 kN. So you will have a new value ng ultimate load natin na 64 kN. So for this, from this one, yung mga bagong factored loads natin, dito natin i-design yung beam natin. So with that, apply yung superposition method natin. Since eto, equal naman yan sa pagkuha ng maximum moment natin na pag ganito, kung ano yung moment nung you simply supported, at saka yung plus kung ano yung maximum moment nung distributed dito sa at midspan. Since superposition method, parehas lang naman yung kalalabasan kung i-apply natin yung structural theory, so ganun yung gagawin natin dito. So the value of your MU max, that is equal to, simply supported tayo, that will become WU L squared over 8 plus yung maximum moment natin kapag concentrated load acting at midspan, that is PL over 4. So isa-substitute natin yung mga values natin. WU, we have 14.4. Yung L natin, that is 6 squared over 8 plus yung PU natin, which is equal to 64 kN multiplied by the length of 6 over 4. So the value of your MU max is now equal to 160.8 kN meter. And after that, for the next step, we will going to assume the value of your rho and we're going to establish yung mga dimension ng beam natin. So let's say, kailangan kasi natin yung rho para makuha natin yung dimension. So let's say na yung rho natin or assume natin that is equal to 0.60 or 60% of rho max. Rho max natin in tension coil. Rho max natin at TC. So with this, yung rho max natin dito, TC, that is equal to 0.85 F prime C beta over Fy multiplied by 3 over 8. Okay? So with this one, yung beta natin lang naman yung problema dito. We will going to refer NSCP 2015, yung limiting value that is 28, yung actual natin that is 27.5. So beta, that will be equal to 0.85. So 0.85 lang yung beta natin. 0.85. Value ng Fy natin, that is 415. Value ng F'C natin, this is equal to 27.5. So you will have a value of your raw max, which is equal to 0.01795. And with that, hanapin natin yung 0.60%. 60% ng 0.1795. So you will have a value of your rho which is equal to 0.01077. And with that, makukuha natin yung mga dimensions natin sa tulong ng value ng rho natin. So sir, ano po yung gagamitin natin dyan sa pagkuha ng mga dimensions? So gagawin natin is yung MU max natin na nakuha natin dito sa loads natin. So we're going to equate that to our formula, which is yung reduction factor natin multiplied by R sub n BD squared. Sir, ano po yung value ng nominal resistance natin? That is rho. Nominal resistance natin, that is rho Fy. And then, lagay lang natin yung BD squared. Rho Fy multiplied by 1 minus rho Fy over 1.7 F prime C. So, etong formula natin dito, etong rho Fy at saka etong naka-parenthesis na 1 minus rho Fy over 1.7 F prime C. That is the formula natin in the nominal resistance natin, which is denoted by R sub n. So, substitute natin yung mga values natin, yung rho, yung MU max natin, that is 160.8. So, from kilonewton meter, lalagay natin siya sa formula. So, kailangan maging Newton mm yan. So, magta-times 10 raised to 6 lang tayo dito. Is equals to, so yung reduction factor natin, since nasa transition control tayo, i-assume natin na nasa transition control tayo. So, we have 0.90. And yung rho natin, that is equal to 0.0177. Yung Fy natin, that will be equal to 415. And then BD squared. Let us leave that at as BD squared. 1 minus yung rho natin, that is 0.01077 multiplied by Fy na 415 over 1.7 na F prime C na 27.5. So by ship solve, we can now calculate for the value of your BD squared. So what will be the value of BD squared? That is 44.20 times 10 raised to 6. Next, meron na tayo dito ng BD squared. So we will just try a value ng B natin o yung width ng beam. So let's say, let us try na B is equals to 250 mm. So with this formula, so makukuha na ngayon natin yung effective depth natin. Therefore, yung D natin, that will become the square root of 44.20 times 10 raised to 6 over 250. So yung value natin dyan, that will become equal to 420.48. Kaso nga lang sa mga dimensions natin, that is always divisible, usually by 50. Para hindi mahirapan sa pagme-measure yung mga ano natin, yung mga construction worker. Kasi kailangan divisible by 50 sila para hindi sila magkamali. And para mas maging accurate tayo. So with this, divisible by 50 tayo, we will just raise that to 450 mm. So meaning to say, yung actual depth natin o yung buong taas ng beam natin, meron tayong 450 mm na effective depth plus the value ng concrete cover natin na 50 mm. So assume natin na yung concrete cover natin that is 50 mm. So you will have a value of your total depth which is equal to 500 mm. So with that, we will now try yung cross section natin na 250 mm by 500 mm. So with that, for the next step natin, we will now consider etong weight ng beam natin. So kanina, kunin muna natin yung weight ng beam natin. So that will become, so usually yung ano natin dyan, that is 24 kilonewton per cubic meter. So para maging uniformly distributed load dyan, we're going to multiply yung cross section or yung area ng beam natin. So kunin na ngayon natin yung area niya. So you have a 250 mm or 0.25 meter multiplied by 0.50 meter. So you will have a weight of your beam which is equal to 3 kilonewton per meter. Ngayon gagawin natin is, since na-design natin yung beam natin, ilalagay na ngayon natin yung weight ng beam natin sa pagkuha ng bagong maximum moment natin. So let's say meron tayong MU max prime. So kapag naka-prime tayo, idadagdag na natin yung maximum moment caused by the uniformly distributed load due to the self-weight of your beam. So yung dating MU max natin, that is 160.8 plus yung madadagdag na weight ng beam natin. So with this, yung formula lang naman natin kapag uniformly distributed load. So pag ganito kasi yan, ayan. Diba, dadagdag lang naman yung weight ng beam natin. So that will become WL squared over 8. Kaso nga lang, since ultimate strength design yung ginagamit natin, magkakaroon tayo ngayon ng factored form. So that is 1.2. And then W, what's the value of your W? L, that is 6 meter squared over 8. So yung value ng MU max natin, that is now equal to 177 kilonewton meter. So with this, meron na tayong value ng MU max prime natin. So gagawin natin is from this new value ng MU max prime natin, we will now design yung steel reinforcement natin in tension. So we'll now compute for the tension. So let's say MU, that is yung reduction factor natin. So yung Rn natin, BD squared. Or equal to reduction factor, yung Rn natin, that is rho Fy multiplied by 1 minus rho Fy over 1.7 F prime C. Multiplied by, ito yung formula natin for the nominal resistance, multiplied by BD squared. So with that, substitute lang natin yung mga values natin. So you will have 177 times 10 raised to 6 Newton mm is equals to, we have 0.90 yung rho natin. Ito yung hahanapin nating value ng rho. So that is multiplied by yung Fy natin na 415. Ngayon, meron na tayong value ng BD squared natin, which is 250 by 450 squared. Multiplied by 1 minus yung rho natin, yun yung hahanapin natin, multiplied by 415 megapascal over 1.7, yung F prime C natin na 27.5. So by shift solve, we can now calculate for the value of your rho, which is equal to 0.0103. So kung meron kong value ng rho natin, by means of yung formula natin, rho is equals to AS over BD, we can now calculate for the value of your area of steel reinforcement. So AS is now equal to rho multiplied by yung B multiplied by D. So you will have rho na 0.0103. Yung B natin, that is equal to 250 mm multiplied by the effective depth of 450 mm. So yung area ng steel reinforcement natin, that will be 1158.75 mm squared. So with that, meron kang total area ng steel reinforcement. So pipili na ngayon tayo ng bakal na gagamitin natin. So let's say, we're going to use yung 25 mm na diameter bars. So sa pagpili ng bakal natin, it depends kung saan ka makakatipid. Okay. And of course, you are going to consider then kung ilang rows yung reinforcement natin. Kasi there is a certain criteria para magsabi natin na magkakasya yung bakal natin dun sa loob ng cross-section ng beam natin. So yung one of the criteria is makakapasok ba yung mga aggregates natin in between dun sa mga reinforcement natin. So later on, we're going to discuss yung mga placing ng mga reinforcement natin dun sa beam cross-section natin. So with that, sabihin natin, we will going to use 25 mm diameter bars. So with that, para malaman natin yung bilang ng bakal natin, that will be yung buong steel reinforcement natin na 1158.75 mm squared. So i-divide natin yan sa area ng isang bakal na merong diameter na 25 mm squared. So you will have a value ng N natin which is equal to 2.36. Kaso nga lang, wala ka namang malalagay na butal na bakal. That's why, yung ilalagay natin dyan is lagi tayong nag-round up. So you will have 3 pieces of 25 mm diameter bars. After that, meron na tayong bilang ng bakal na kinakailangan natin dito sa beam natin. So with that, we're going to check yung ductility natin. Sir, bakit po natin check yung ductility natin? Para malaman natin kung doubly reinforced ba yung beam natin or singly reinforced yung beam. So paano natin i-check yung ductility? Kunin natin yung raw actual. We're going to compare that to the raw max and to the value of your raw minimum. So kailangan yung raw actual natin that is greater than to raw minimum but less than to the value of your raw max. So kunin natin ngayon yung raw actual natin, that is AS over BD. Ito mismo yung actual na ilalagay natin. So meron tayong 3 peraso ng steel reinforcement na ilalagay na merong diameter na 25 mm over yung width ng section ng beam natin that is equal to 250 multiplied by the effective depth na 415. So you will have a value of your raw actual which is equal to 0.0131. Next naman is kunin natin yung value ng raw minimum natin. So that is equal to 1.4 over Fy. So raw minimum is now equal to 0.00337. Next naman, yung isa pang formula natin for raw minimum, that is equal to square root of F prime C over 4 multiplied by Fy. So yung value natin dyan, that is equal to 0.00316. So between the two formulas sa raw minimum natin, we will going to adopt yung larger value. So yung raw minimum natin, that will become 0.00337. Next naman, using we can now say, dun sa pag-aano natin sa mga values natin, so yung raw actual natin, at saka yung raw minimum, at saka yung raw max natin. So we will just compare yung tatlong yan, and kapag nasatisfy natin yung condition, when it's say ductile yung beam natin. So if we were going to check, mapapansin natin na ito yung conditions natin. Therefore, ductile failure. Therefore, yung gagawin natin dito is singly reinforce yung beam natin. So, magiging safe yung beam natin kapag 250 by 500 yung dimension ng biga natin. So for that, paano natin i-check kung magiging safe ba or hindi? We will now check yung flexure natin. So yung dadalhin na moment, maximum moment ng beam natin, that is 177 kN meter. Ngayon, we will now going to check kung ano yung magiging design moment capacity ng beam natin. Na merong dimension na 250 by 500 mm. So we're going to check now yung capacity natin. MU capacity. So that will become yung rho natin. We will now assume that na 0.90. Yung rho Fy natin, yung rho natin na nakuha kanina na actual, that is 0.0131. Yung Fy natin, which is equal to 415. Yung B natin na 250, yung D natin na 450 squared, 1 minus yung rho natin na 0.0131. Fy is 415 over 1.7. Yung F prime C natin na 27.5. So yung value ng MU capacity natin o yung capacity ng biga natin, that is 218.90 kilonewton meter, which is greater than to the value ng MU max natin, which is equal to 177 kilonewton meter. Meaning to say, safe in flexure yung beam natin. So we will now going to adopt 250 by 500 mm. Reinforce with 325 mm diameter bars at midspan. Sir, bakit po at midspan yung location ng bakal natin? Kasi nga at midspan, doon yung location ng maximum moment natin. So, doon natin i-reinforce yung beam natin.